Next, we're going to talk about the mathematics behind how ANOVA works so that we can perform this hypothesis test for whether or not all the means are equal, or perhaps at least one pair of means is unequal. We're also going to spend a considerable amount of time looking at some intuitive aspects for ANOVA so that you understand why the mathematics works. Okay, now for this entire section, we're going to be focusing on one example, dealing with Wheaties. For those of you who do not know, Wheaties is a type of dry cereal that you can purchase at most grocery stores in the United States. And this particular cereal is well known because of what it puts on the cover of its cereal box. Typically, they put athletes on their box as, I guess you could say, a marketing ploy to get people to buy their type of cereal. And so Wheaties spends a lot of time then developing the covers of their boxes. And so let's say, let me get my red pen out here. Let's say the company that makes Wheaties, General Mills, wants to test 4 new different box designs. We'll just call them design 1, 2, 3, and 4 that they want to use in general throughout all grocery stores that sell Wheaties. And to do this test, they choose 10 grocery stores with approximately the same sales volume, and these are going to be our experimental units. Each store is going to be randomly assigned one of the package designs. Other relevant conditions, such as shelf space, the location on the shelf, is kept constant across all stores. And what our data is going to consist of is the number of cereal boxes sold in 1 month at each of these corresponding stores. So let's let y sub ij be a random variable denoting the number of cereal boxes sold in a 1 month period of time, where the I subscript, so that very first subscript, is going to denote the design type. In other words, this is going to be our factor levels. We're going to have factor levels 1, 2, 3, and 4, which, for the lack of a better name, design 1, 2, 3, and 4 it means. And then the J subscript, that second subscript, is always going to denote the store within a particular design type. So, for example, let's say we go and perform the experiment, then we actually observe for design 1, store 1, we observed 12 cereals were actually observed for this 1 month period of time that were sold. For store 2, that's for design 1, we observed 18 cereals that were sold. If we come over here to design number 2, store 1, we observed 14 cereals. And so again, we have a total of 10 different stores as our experimental units. So we have 10 different observations here. Now, at the bottom of the table, we have essentially the sample means by design type. So similar to what we've done before, we put a bar on top of the Y. And because we need to say, well, what design we're talking about, we have design 1, 2, 3, 4. But since we have the second subscript now in this notation, and essentially we're summing over that subscript to find the sample means for each of the design types, what I'm going to do is put a little dot in place of that J subscript. This is very common notation that people use. So for example, Y bar sub 1 dot is the sample mean number of cereals for design 1. It's equal to 15. We're going to let N sub I denote the number of experimental units per design type. So for example, for that first design type, we only had 2 stores. N sub 2 was 3 because we observed information from 3 different stores. So then we can put this all into the context of this terminology that we've been talking about. And our response variable is the number of cereal boxes sold. Our factor is the cereal box design. It has factors of levels of 1, 2, 3, and 4. Our treatments are also 1, 2, 3, and 4. Remember, our treatments will be exactly the same as factor levels, at least in our class. It's not until you get to multiple factors for a particular experiment or do treatments mean something different from factor levels. And then our experimental unit is the actual grocery store. That's what we're making our measurement upon. Each grocery store, we're looking at the number of cereal boxes sold. So in analysis of variance then, for this particular situation, we're interested in the following hypotheses. The null hypothesis is that the mean number of cereal boxes sold for design type 1, 2, 3, and 4 are all equal to one another. So for example, this mu1 basically represents like a large population number of stores that would have, let's say, design number 1. Mu2 will be a large number of population stores that would focus on design number 2, and so on. Obviously, that would be very costly to apply this to a large number of stores. So instead, what we did was we applied design type 2 stores, design type 2 to 3 stores, and so on. Now, the alternative hypothesis in at least one pair of these means, population means, are different. Well, what does it mean, though, in the context of this problem, then, if we don't reject HO? Well, that says that there's not sufficient evidence to show that there's a difference between population means. Meaning, well, if there's not enough evidence to show that one design is better on average than others. They may be, yes, but at least from our information that we have actually observed in our sample, we can't say that one is necessarily better than the other. And just to make sure this is clear, what General Mills would actually like to do is find out, well, which design is going to result in the highest mean number of sales or highest mean number of boxes sold for a store. And so they want to pick that particular design. Sorry if that wasn't clear. Now, if we reject HO, this means at least one pair of population means are different. This means that some designs are better than other designs on average. And from a company perspective, we want to find this out, and then we would want to choose those designs or the design that results in the highest mean number of sales in the end. Another section of our notes corresponding to ANOVA will help us figure out that once we do reject HO, well, which, in this case, which design, or in general, which factor level would be, let's say, best. So whenever you have then a data set like this, or you go out and collect it, you go out, perform the experiment, get your data. We've already seen the data in this particular table. Once you have that, then you want to get the data into R, and the first thing you should do is some plots. So let's go ahead and do that. So my data is in Wheaties.csv. It's a comma delimited file. I put it into an object called Wheaties. And here's my data. We've already seen it. Now, normally I would do a box plot or do box plots with dot plots on top of them. But box plots here are not going to be very informative because in some cases for these design types, we only have 2 observations. So instead, I'm just going to do the dot plots. And so to do this, I use the strip chart functions we've done many times before. So what's going to go on my y-axis is the number of boxes sold. What goes on my x-axis then is the corresponding design type. I'm going to use a line width of 2, meaning the plotting points are going to be 2 times its, let's say, thick in terms of the lines in the plotting points, 2 times the thickness than what's normal. They're going to be red. I'm going to jitter the lines jitter the points to avoid overlapping points. I'm going to draw the plots vertically. I'm going to use a plotting character of 1, which corresponds to an open circle. And then I'm going to put a title on my plot and y and x-axis labels. Okay, here's the plot then. So again, number of boxes sold. Here's the design type. And immediately what we can see here is for design number 4, all the data seems to be shifted higher than for all the other design types. And so immediately you might be thinking, hey, something's going on here. Maybe design type will be for a larger population of grocery stores. It'll be better in that situation, because what my sample's telling me is that, at least in the sample, the sales are higher for design type 4 than any other design type. Again, we have a small sample size here, so it's hard to necessarily make that generalization just from this plot, but at the very least, it should get you thinking about it. And we also see design number 3 too. It's shifted above 2, and if you compare it to 1 there, we can see it has shifted a little bit higher than where 1 is. And so that might make you think, well, maybe 3 is better than 1 and also better than 2. We'll look at that more formally as we go. Okay. We can also find then the sample means by design type 2. So we've used the aggregate function before to do that. What I want to aggregate is my response, the number of cereal boxes sold. I want to do it by design type. My data is in Wheaties, and the fun function I'm going to work with is the mean function. And so we can see that for design type number 4, on average, 27 boxes of cereal were sold. For 2, only 13. You can also do a similar thing here for the standard deviation 2. Okay. So what we would like to be able to do is now take this information from the sample and determine if this sample gives us enough information to say that indeed the population means would be different. That's what we are trying to do. And to do this, we're going to use this statistical procedure called analysis of variance, or ANOVA for short. So what an analysis of variance does, it looks at different measures of variance to make a judgment of, are the population means different? So we're going to look at actually 3 different measures of variation, or variability. The first one's called typically the within sample variation. And what this is essentially going to do is going to look at every single observation that we have. So let me go back up here to my data. I'm going to do some erasing. Oops. Going to look at every single observation we have, and we're going to compare it to its corresponding mean for that factor level, or in this case, the cereal box design type. So it's going to compare 12 to 15. It's going to compare 18 to 15 to see how much variability there is. And when we first started looking at a sample variance, how did we do that before? Well, we would do it like this. Take 12 minus 15, square it, plus 18 minus 15 squared, and then we would form an average value by dividing by n minus 1, which would be 2 minus 1 in this particular case. That's how we would do it. Well, we're going to now do that same concept here. We're going to do it for design 1, and then for design 2, we're going to compare 14 to 13, 12 to 13, and so on. Now get back to where we were. And what this means then is within sample variation. So essentially, maybe the name's not the best, but within a particular design type, what kind of variation or how much variation do we have? And then by finding the average value, we're going to then come up with what we're going to refer to as the mean square error, or MSE for short. So here's the actual formal expression. Let me make this a little bit bigger here. Okay, so we have a sample size 2 for design type 1. And what we're going to do is we're going to take each of those y values, subtract off its mean, square it. So this is for design 1. For design 2, we're going to do exactly the same thing. Remember, we had 3 observations for design 3. take that observation, subtract off its mean, square it, add it up. Design 3, design 4. We could then also, to get that average value, we take it divided by, well, that number of observations minus 1 for design 1, number of observations minus 1 for design type number 2, and so on. Let's combine everything, write it in a little bit more compact form. So now, since I'm basically doing the same thing for every design, how about we put another summation symbol out there? And instead of putting the design of 1, design 2, design 3, and design 4 there, how about we just write that as the letter I instead? And then if we combine everything that's in the denominator, then in a general form, what we get here is n1 plus n2 plus n3 plus n4 minus t. T, in this case, will be 4, and I should have said that before. And remember, what t represents is essentially the number of factor levels that we're working with. So let's start plugging in numbers, and that's what I do next. And if you go through all the math, you get 7.67. Okay. Now, let's talk a little bit more about where this name mean square error comes from. And it comes from the following. Suppose we wanted to predict the value of y sub ij. In other words, for design type I, store j, I want to know how many sales should there be? And one way then to predict what it would be is simply, how about we use a sample mean? So if I had a sample of stores for design type I, find the mean, that seems like that would be a reasonable way to predict what an individual store would be. It's not going to be a perfect prediction, no. And how do we then judge how perfect it is? Well, we actually observe what that number of sales would be, subtract off its predicted value, we square it, and then let's get a measurement of the amount of how far we're off in this prediction across all the stores, all the design types. And thus what we have here is a measurement simply of, I'm taking the sum of squared errors. So if we think of how far y sub ij is from its predicted value, that's like an error. So I have the sum of squares for errors. Some people will call it sum of squared errors instead. People often abbreviate this as SSE. So we have MSE, which is like the average squared error, and then we also have SSE as well. So that's the first kind of measure of variability that we're going to look at with respect to ANOVA. Here's the second. Something called the between sample variation. Again, maybe that's not necessarily the best name out there, but this is the name people often use. And now what we're going to do is we're going to look at each of the sample means for the design types, or the factor levels to be more general. And we're going to compare it to the overall mean, which I denote by y bar dot dot. So let me actually go back up to my data once again. There we go. I'm going to do some erasing once again as well. And so what this between sample variation looks at is this. Let's compare 15 to what the overall mean is, which is, let me see if I have it, I think it is 18. Yes. So the overall mean of all 10 of those numbers, meaning these 10 right there, is 18. So what we're going to do is look at how far is 15 from 18, how far is 13 from 18, how far is 19 from 18, how far is 27 from 18. So you can see again, if I were to square it and maybe somehow come up with an average value, that would be another measure of variability. And in fact, it is. So let me go back to where we were. Here we go. Now, what we're also going to do is weight all these measures of variability by the number of observations within a particular factor level or design type for us. It seems like to make sense because, let's say if you have a situation where you have only 2 observations for a factor level, in another case where you have 100 observations. Well, you would think that that case where you have 100 observations should be, let's say, weighted more because there's more observations there. And so with that, what we can do is as follows. We can calculate what's called the mean square for treatments. So for design type 1, we're going to have our weight of our sample size, which will be 2. Take that sample mean for design type 1, subtract off the overall mean, square it. Then for design type 2, we'll weight it by the number of observations there, 3. We take that sample mean for design type 2, subtract off the overall mean, square it. And we're going to keep on adding all this up for design type 3 and design type 4. To get an average value, we're going to take the number of design types or factor levels in general, t. We're going to take that, which is 4 for us, minus 1. Okay. So we can write this in a little bit more compact form then using a summation symbol. And now if you were to plug in all the numbers to where they belong, eventually then do some more math, you get 86. Okay. So why is this called then mean square for treatment? Well, remember how factor levels, at least for us, are the same thing as treatment. So we're looking at how far off are all the treatment means from the overall mean. So that's where that name comes from. Let's see, so now we're on bottom page 7. And we can also think of it in terms of this prediction as well. So, if I didn't have any other information other than, let's say, the overall mean sales for all the 10 stores, it would make sense then that if I want to predict how an individual design type is going to do at a set of stores, it seems to make sense that I would try to predict that with that overall mean. And so now what we're looking at then is, let's say, what we actually observe, subtract off what we would predict by. We square it, we weight it by the number of stores per design type, and we sum over all the design types. This measure, which is in the numerator of our mean square for treatment, or MST, this numerator has a special name. It's called the sum of squares for treatment. Some people call sum of squared treatment as well. People often abbreviate then as SST. So here are some plots to help demonstrate what's going on. Let me make this smaller now. So here's our exact dot plot that we had before. But now I have plotted y bar dot dot. And here are all the design type means. So there's y bar sub 4 dot. Sometimes it's hard to say this stuff. And so I've tried to annotate these plots to help you see what's going on. So we just talked about SST or MST, mean square for treatment, SST, sum of squares for treatment. And what that's measuring is what's illustrated here, where, again, here is the overall mean, and we're always looking at how far is that design type mean from the overall mean. And so, again, this gives us a measure of variability when we compare each design to the overall, you could say, experiment as a whole. Now, in terms of SSE, sum of squares for error, or MSE, mean square error, the top plot on page 9 helps demonstrate what's going on there, where we're always looking now within a factor level. How far is a particular observation from the corresponding factor level's mean? Now there's one more source of variation that we, or measure of variation that we're going to talk about. So this is the third one. And that's what's called the total sums of squares for the experiment. Let's say the total possible variability that exists. And what that is simply take all your observations, subtract off now this overall mean, squared, and these summations then allow me to do this mathematical calculation across all observations. My total sums of squares is often abbreviated as TSS. And there's a very interesting relationship between the total sums of squares, the sum of square errors, and the sum of square for treatment. And that is, if I were to take SSE plus SST, I get TSS. And so that's kind of interesting. And so basically what we did originally with this first and the second measure of variation, essentially what we're trying to do is partition the overall variation that actually occurs in our experiment. Okay? And here's a mathematical representation of this. If this course that we were doing right now was more mathematical in nature, like what a statistics major would actually take, you would actually be required to prove this. You can actually go through the algebra to prove it, this equality. Okay, so reasons for calling all of this ANOVA, analysis of variance, or ANOVA. I know analysis of variance isn't ANOVA, but you can see where the AN comes from analysis, for example, and the VA comes for variance. Anyway, so the reasons why we call this analysis of variance is that what we're doing is looking at components of the overall total variance. And by measuring or by examining MSC and MST, ANOVA methods can be used to determine if all the means are equal or at least one pair is not. And what we're actually going to do is this. We're going to calculate a statistic, which we're going to call F sub obs. This is essentially going to be our test statistic. I'll explain why it's called that there later. Obs corresponds to observed value. What we're going to do is compare these two measures of variation by taking their ratio. If this ratio ends up being large, we're going to reject HO. There is a difference among the means. If this ratio is small, well, there's not sufficient evidence that there's a difference among the means. Now, to help you see why we make that judgment, what I've done is set up an interactive Excel file that we're going to use here that will allow you to see when we would reject HO and when we wouldn't. And the purpose here is to give you an intuitive feel for what's going on. Okay. So I have some screen captures here that will demonstrate it, but we're going to actually enter some of this information in here. Oops, let's do this first. Okay. So what I have here is essentially the table that we saw earlier that had our data and also the sample means for each design type. And I've set up the data, though, in a way that we could easily change the data to see what would happen. I'll explain that in about 30 seconds. What I want to show you over here is that we have this dot plot. And instead of drawing it vertically, I drew it horizontally instead. But this is essentially the same kind of dot plot that we saw earlier, where now the overall mean, that y bar dot dot, sorry, my notation is a little bit off there, is denoted by this particular line there. And then I have each of the corresponding design type means represented on the plot by these blue lines. And then the observations are denoted by the plotting symbols themselves. Let me erase that. Okay. So this is essentially the same plot that we saw before. Now I'm going to change the data values. And I'm going to do it in a simple way. Hold on here. Fortunately, my Excel has frozen up. Just give me a moment. Now I have this file set up so that we can make some changes to our observations so that we can see what is going to be the effect on our overall conclusion of if we reject or don't reject HO. And I guess, sorry, before I actually do that, what I've done down here below in this table is I've done some calculations. So for example, SSE is 46, MSE is 7.67, MST is 86. And if we take that ratio that I was talking about before, MST divided by MSE, we would actually get 11.22. So if we take 86 divided by 7.67, we get 11.22. And I understand that we haven't talked about yet to determine, well, is this a large value, large enough for us to reject HO? We will get to that shortly. But for now, let's just focus on what the actual numerical value is for F and what I actually give here for the actual decision for the hypothesis test. In this case, we would reject HO. And hopefully that makes some intuitive sense to you that we would reject based upon what we saw earlier in terms of the plot, where how, for example, design 4 seems to have a lot different set of sample values than design 3, 2, and 1. Okay, so now I can come up here to this set of cells in this table. And next to it, I have add to each treatment value. So if I were to add 3 to each treatment value, look what happens to all the design 1 values. They increase by 3. Notice now the sample mean is 18. I'm going to do that for design 2 as well, but I'm going to add 5 to it. For design 3, I'm going to subtract 1. And for design type 4, I'm going to subtract 9. Now, this mean set of cells is automatically updating corresponding to this new set of data that we have. And look at this. All the means for each design type are exactly the same. And look what happens, if you see where my mouse is, look what happens to our data. Now we have this great amount of overlap between design 4, 3, 2, and 1. And if I were to show you this plot, hopefully you would say, okay, well, it looks like, pretty much what we see in the sample, everything's about the same. There's probably not going to be much differences amongst the stores at all. And you would probably conclude, yeah, I bet we're going to say, there's not sufficient evidence to indicate a difference among the means. Now, the calculations that are down here in the table automatically also update based upon what I have when I added those values to each of the sample values. And so F obs now happens to be 0. And then, again, I know we haven't talked about how to determine what's large and what's small. But what we can see from this result here, now we don't reject HO. And so that, seems to make sense based on what we see in this plot. But now this is now on page 12. Let's make another change to our data. Instead of subtracting off 9, how about we subtract off now only 5? So now the mean happens to be 22 for design type 4. And what we can start seeing is that, well, design 1, 2, and 3 are very similar. But now design 4 seems to be shifted up a little bit. And so again, that might make you think, okay, something's maybe going on here. Something's maybe a little bit different about design 4. But I don't know really if that's enough information to say, yes, truly indeed that there is a difference in the population mean sales for design 4 versus all the rest. Also down here, we can see MSE, we can see MST. F now has increased to now 1.11. But if we were to do the formal hypothesis test, we still would say don't reject HO. Let's move on to the next page. Let's look at page 13. Now suppose, suppose now I only subtract 2. Look what happens to the plot. Look what happens to the F obs value and also the decision. Okay, now we see my data has increased in value. My sample mean is higher, it's 25 now. And we can see, again, more of this shift in this set of values for design 4 in comparison to everything else. MST has changed. Look at FOBS. That has increased even further. Now it's 3.41. But still, it's not enough evidence to say, yes, indeed, the population for all the stores, for all the stores here, that design 4 would have a larger mean sales than design 1, 2, and 3. And lastly, how about now we just have a 0? So now I have my original data values for design type 4. Again, excuse me, design 4 has shifted even higher. It doesn't overlap at all with any of the data values from the other design types. MST is now 43.2. FOBS has increased even further, 5.63. And look at this now. Now we reject HO. Now there is sufficient evidence that indeed the population means are different. So again, the purpose of this demonstration here was to help you see the relationship between MST, MSE, relative to this particular plot and relative to the decision that one would make. The more differences that we have amongst these sample means, the more likely we are going to say, indeed, the population means are different. We can see, and by seeing this visually, by seeing how these numerical values update themselves or change for the different observed values, hopefully this will give you some intuitive feel for what analysis of variance is actually doing. Okay, so that takes us then to the bottom of page 14. So again, this statistic here, MST divided by MSE, is going to play a very important role for us. That's what's going to help us to know, is there sufficient evidence to indicate that the population means are different? Since we're going to actually make a comparison of the statistic to the F distribution, we're going to call this FOBS for observed value. Now, normally what we would do in this particular case, because this would actually be a calculated numerical value, we would typically call this a little f there. It's just more standard practice to say, okay, this is what we call f, since we're going to compare it to an F distribution. So people typically use a capital F. So I guess I compromised our notation a little bit, and I decided to call FOBS to indicate that this is the actual observed value that we're going to be working with. Okay. Now, let's see now. I think I've covered that. Yes. Okay. So there's also some more, I guess, statistical, mathematical reasons for why this all happens or all works out. And that is, if we think of, let's say, MSE and MST actually as random variables. So we work, let's say, with the capital Y's with them. Then one could write out this, that the expected value of MST is equal to the expected value of MSE if that is true, that the population means are the same. So, you know, if you were to then look at the ratio of these two things, of course, you would get 1. That's why we look at MST divided by MSE. I know I wrote it in terms of expected values, but still, you know, it makes some sense for why we look at the ratio. Now, though, suppose the population means are not equal. Now what happens is this. This corresponds to this right here. Now the expected value of MST is actually greater than the expected value of MSE. And what does that mean then for the ratio? It's going to be greater than 1. So in other words, then when we actually observe MST, we observe MSE, if that ratio is greater than 1, that says, okay, now there's something going on. And if it's greater than 1 enough, then we're going to say, hey, we're going to need to reject HO. Well, how do we make this decision then to reject? Well, if we now again think of MST divided by MSE as a random variable, it actually has an F distribution corresponding to it. And so we've got to be careful with our notation. I know it can be confusing. Here, think of as a random variable, RV for random variable. So the statistic here has an F distribution. So that means then that, if the null hypothesis, and this is if the null hypothesis was true. So let's say that this is the F distribution. It's going to look something like this. It's not a perfect diagram. So what that says then basically is that if I observe, let's say, F obs somewhere in the middle here, where there's a lot of probability underneath that curve, that would be a reasonable thing to have happen if the null hypothesis was true. But instead, let's say I'm way out here, where there's very little probability in terms of the, and that's where F sub obs actually ends up being. Then that should tell you, well, wait a second. It would be very unusual for me to get a value of F obs this large if the null hypothesis was true. So I wouldn't be surprised then if the null hypothesis is not true. And that's the logic that we work with. It's the same logic that we work with any hypothesis test. So since this statistic here has an F distribution, we can find probabilities associated with a particular with this particular distribution, the F distribution. The numerator degrees of freedom is going to correspond to, for MST, remember in terms of its denominator, it has t minus 1 in it. That's going to be the numerator degrees of freedom. In the denominator of F obs, remember MSC itself, you're going to take that sum of those squared errors, divide by and what ends up being the overall sample size minus the number of treatments or number of factor levels. That's how we find the numerator and denominator degrees of freedom for the F ob statistic itself. Okay. So what we can do then is go to the F distribution, find a quantile with it. And again, we typically use a small alpha there because that means there's a little probability that you're going to be to the right of this critical value. And we use then this quantile as a way to make the decision is our F obs unusual or not. We could also calculate a p-value just like what we would in any other case. Here we're using an F distribution for it. Small p-values, meaning that let's say the probability that x, if x is a random variable that is has this corresponding F distribution, the probability that x is greater than whatever we observe F obs to be. If that is small, then reject the null hypothesis. Okay, so the purpose of this discussion was to give you some of the mathematical details of how analysis of variance work. Again, we're comparing a number of different measures of variability. Also, the purpose of this discussion was to give you some intuitive feel for what's going on. So we saw that dot plot. We saw with that interactive Excel file that when we make changes to our data, we see how that affects the dot plot. We see how it affects our statistic of interest as well.